In this video, we'll talk about continuity and exactly what a continuous function is. A function is called continuous at a point a if the limit as x approaches a of f at x is equal to f at a. Basically, what this means is that if the function takes on the value that the function thinks that it'll take on as it's nearby, then the function is called continuous. In order for a function to be continuous at a, it is necessary that the following three things are true. First of all, f at a must exist. It must be a defined quantity. A must be in the domain of the function f. Second, the limit as x approaches a of f at x equals L must exist. So the limit on the left side of this equation must exist. In order for that to happen, both of the one-sided limits must exist and be equal to each other. The third condition is that f at a and L must be equal to each other. If a function is not continuous, then we say it's discontinuous. If a function is continuous at every number on an interval, then we say it's continuous on the interval. If we say a function is continuous without specifying an interval, we usually mean that the function is continuous at every number in the domain of the function. The best way to understand continuity is to talk about discontinuity. In what ways can a function fail to be continuous? Well, let's talk about the different kinds of discontinuities that you might see. The first one we want to talk about is what's called a removable discontinuity. If the limit as x approaches a of f at x exists but does not equal f at a, then the discontinuity is called removable. For example, consider the function f at x equals x squared minus 4 over x minus 2. This function has a removable discontinuity at x equals 2. In fact, this function has a graph which is almost a line. It's a line except it has a hole in it at x equals 2. That's because we're dividing by x minus 2. Consequently, x equals 2 is not in the domain of the function. If x isn't equal to 2, then x squared minus 4 divided by x minus 2 reduces to x plus 2. So this equation is y equals x squared minus 4 over x minus 2, but this reduces to x plus 2 provided that x is not equal to 2. So this graph is the equation of a line, except it has a hole when x equals 2. Because there's a hole there, f at 2 is not defined, and therefore the function can't be continuous. However, the limit does exist. The limit as x approaches 2 of f at x is 4. That's something you can see from the graph, or you can see from the formula. As x is getting close to 2, then the y values are getting close to 2 plus 2, which is 4. Removable discontinuities like this occur when the limit as x approaches a does exist, but it's not equal to f at a. That can either happen because a is not in the domain of the function, so f at a doesn't exist, is undefined, like in this case, or it could also happen if the limit existed and f at a was defined, but they just didn't equal each other. In a case like this, where there's a removable discontinuity, you find a hole in the graph, and the hole can exist because the function is undefined there, or if it is in some sense misdefined, and f of 2, in this case, was defined to not equal 4. If that were to happen, then there would still be a removable discontinuity here. We call it removable because, in some sense, we can fix it. In some sense, we can fill in the hole. So we already commented on the fact that f at x reduces to x plus 2. If we define f at 2 so that it equals 4, then we would fill in the gap. then we would have that f at x is equal to x plus 2 for all x. We're able to fill in the hole and make the function continuous. That's how this type of discontinuity gets its name. The discontinuity is removable in some way by redefining the function. It's an important but subtle distinction that this function, f at x equals x plus 2, isn't the same as our original function because we've increased the domain. The two functions agree everywhere that they're defined, but the original function was not defined at x equals 2. So we've redefined the function by extending its domain. We've done so in such a natural way that it's easy to forget that these two functions are actually different. You can think of removable discontinuities as fixable discontinuities, that there's a discontinuity, but it's just there by accident. For example, the function f at x equals sine x over x has a removable discontinuity at x equals 0. There's a hole at x equals 0. But we can redefine f by just setting it equal to 1 when x equals 0. The function as it's stated, f at x equals sine of x over x, doesn't have x equals 0 in the domain. So if we extend the domain by defining it at 0, by just simply stating that f at x is equal to sine x over x if x isn't equal to 0, but at x equals 0 we define it to be equal to 1, then now this function is continuous. We've essentially filled in this hole. And now we have a continuous function. But in order to fix the discontinuity, you have to make the right choice when you redefine it. For example, if you redefine the function sine of x over x to be a function called g that's given by the formula that you see here, g of x is equal to sine x over x if x is not equal to 0, and 0 if x equals 0, then this function g is still not continuous at 0. It's continuous everywhere else, but there's a hole at x equals 0. We've redefined the function to give it a value at x equals 0, but in some sense we've given it the wrong value because there's still a hole there. The limit as x approaches 0 of g at x hasn't changed. It's still 1. The y value that it wants to attain is 1. But unfortunately, that's not the same as the value that it does attain at x equals 0, because g at 0 is defined, but it's defined to be something other than what it wants to be. It wants to be 1, but we've defined it so that it's equal to 0. What that means is we haven't removed the hole, so there's still a hole there, and so there's still a removable discontinuity. It's important to understand it's still called removable because we could still redefine the function in a different way to get rid of that hole. Another type of discontinuity is called an infinite discontinuity. In this case, the limit doesn't exist because the values grow or decrease without bound. This type of discontinuity is called an infinite discontinuity because the limit as x approaches a of f at x is what we called an infinite limit. Both of the functions that are displayed here have infinite discontinuities. The function on the left has graph y equals x minus 1 over x minus 2. This is the graph of y equals 1 over x shifted to the right by 2 and then up by 1. The limit as x approaches 2 from the right is infinity, but the limit as x approaches 2 from the left is negative infinity. This is an example of an infinite discontinuity because the one-sided limits are either infinity or negative infinity. The graph on the right is the graph of y equals 1 over the quantity x minus 2 squared. In this case, the limit as x approaches 2 from the left or the right is infinity. Both of these functions have infinite discontinuities at x equals 2. It is not possible to redefine a function at a point to remove an infinite discontinuity, and so an infinite discontinuity is not removable. Another type of discontinuity is called a jump discontinuity. In this case, you have the limit does not exist because the left and right limits both exist but are not equal to each other. So in the picture that you see here, the limit as x approaches a from the right is m. So if we're approaching a from the right, we're on this curve on the top. And the y values are, in this case, are approaching m. If we look at the limit as x approaches a from the left, now we're on the left side, and now we're on the bottom graph, and the y values approach L. So the left limit exists, and the right limit exists, but they don't agree with each other. This is called a jump discontinuity. If f of x equals the absolute value of x over x, for example, then the limit as x approaches 0 from the left is -1. The limit as x approaches 0 from the right is +1. In fact, f of x is always equal to 1 on the right of 0, and it's always equal to -1 on the left of 0. So from the left, it's negative, and from the right, it's positive. A jump discontinuity is not removable because you can't fill in a jump. Notice the way that this function, f of x, is defined. It's the absolute value of x divided by x. The number 0 is not in the domain. That's why you have these two holes at x equals 0. Because x equals 0 is not actually defined. We could try to redefine this function, but we can't make it continuous that way. For example, we could say that f of x is equal to 1 if x is greater than or equal to 0, and -1 if x is less than 0. In the graph, that's symbolized by filling in the hole at the point with coordinates 0, 1. However, that does not remove the jump. It's not possible to have a continuous function when there's a jump, because the function on the left is too far away from the function on the right. In order for a graph to represent a graph of a continuous function, all of the pieces have to connect. There can't be any holes or gaps or jumps. If it's just a hole, you can fill it in, but with a gap or a jump, it's not so simple. In this case, we have what's called a right continuous function, because f at 0 is equal to the right limit at 0. F at 0 is equal to the limit as x approaches 0 from the right of f at x. So this is a right continuous function, but it's not left continuous. We can give these as definitions. A function f is right continuous at a if f at a is defined and equals the limit as x approaches a from the right for f at x. F is called left continuous at a if f at a exists and is equal to the limit as x approaches a from the left of f at x. The only way a function can be both right continuous at a and left continuous at a is if it is actually continuous at a. So this should say is if. So that a function can only be actually continuous if it is both right continuous and left continuous, because in that case the two pieces will meet up. Let's look at an example. Find all values of c for which f is continuous, if there are any. So here we have a piecewise defined function. F at x is defined so that if x is less than 2, x squared minus cx plus 5 is the output value, and if x is greater than or equal to 2, then the output value is minus x squared plus 2x plus 5c. This function is continuous at every value that isn't 2 necessarily, because it's just given by two pieces which are polynomial, in fact quadratic. So if you're looking at just to the left of 2, then you have something which doesn't have any holes in it, or gaps. it's continuous. If you're looking just to the right of 2, then again, you're not going to have any holes. This is just a polynomial. So the graph is continuous. The only place where you might have a problem is at x actually equal to 2, because you need these two pieces to meet up. They need to agree with each other. How can we actually find a value for c where these two things meet up, where the value on the left is actually equal to the value coming from the right? Well, we just compute the limits. So we start with the limit as x approaches 2 from the left. Now, if x is approaching 2 from the left, it's 2 minus something, so that means that x is less than 2. So in this case, we're using the top rule. So it's the limit as x approaches 2 from the left of x squared minus cx plus 5. This is a polynomial, so we can just use the substitution rule to compute this limit. So it's going to be 2 squared minus c times 2 plus 5. Well, 2 squared is 4. 4 plus 5 is 9. So this is 9 minus 2c. That's the limit from the left. Notice that it depends on c. And that's natural because c is in the definition. Now let's compute the limit from not the left, but from the right. The limit as x approaches 2 from the right of f of x. So in this case, we're no longer looking at the top formula. We're now looking at x equals 2 plus something. So now x is greater than 2. So we're using this formula here, right here. So this is going to equal the limit as x approaches 2 from the positive side, or from the right, I should say, of minus x squared plus 2x plus 5c. Once again, we're looking at a polynomial, so that means we can just use the substitution rule. So we just plug in x equals 2. So it's minus 2 squared plus 2 times 2 plus 5 times c. So 2 times 2 is 4, and of course 2 squared is also 4. So this with a minus in front is negative 4. Negative 4 plus 4, those two will cancel, and you'll just be left with 5c. So this term cancels with that term. Okay, so the limit from the left is 9 minus 2c, and the limit from the right is 5c. Now, in order for the limit to exist as x approaches 2, these two things have to actually be equal to each other. So we need 9 minus 2c to equal 5c. And now we just solve for c. So we can add 2c to both sides. And we'll have 9 is equal to 7c. So if you divide by 7, you get that 9 over 7 is equal to c. So this limit exists if c is equal to 9 over 7. Now that tells you that the limit exists. We also know that f is actually defined and equal to that at x equals 2 because of this condition right here. We know that f at x is equal to minus x squared plus 2x plus 5c if x is actually equal to 2. So the limit, just to check, as x approaches 2 of f at x is going to be equal to, well, what's it actually going to be? We can just plug in c equals 9 over 7 into either of these and we'll get the same thing. So it's going to be equal to 9 minus 2 times c, which is 9 over 7. So what's that going to be? That's 9 minus 18 over 7, which is equal to 63 over 7 minus 18 over 7, which is equal to 45 over 7. So that's the limit as x approaches 2. If you actually compute f of 2, now if x is equal to 2, then we use this rule on the bottom, which is minus 2 squared plus 2 times 2 plus 5 times the c value, which we've determined is 9 over 7. And just like before when we were computing using the bottom rule, this -4 and this +4 cancel, and you're just left with 5 times 9 over 7, which is 45 over 7. So what we've shown here is that the limit as x approaches 2 of f at x has the same value as f at 2, so the function is in fact continuous. Now if you actually look at the definition, the way this was defined, each of these individual pieces is continuous. The only place where you might have an issue is x equals 2. In order to be continuous, the two pieces of the graph have to meet up at x equals 2. But if you just look at each piece individually, we know that this piece here, when x is less than 2, is continuous everywhere. But we're not letting it actually use this rule when x is equal to 2. However, we are using the bottom rule, minus x squared plus 2x plus 5c, when x is greater than or equal to 2. So right away, I know that this is right continuous, but it's not left continuous. In order to be continuous, it needs to also be left continuous. So we need to find the value of c so that these two things are equal. Well, let's look at a graph. When c equals 2, the function is not continuous because the piece on the left doesn't meet up with the piece on the right. So the left limit does exist and the right limit does exist, but when c equals 2, the left limit and the right limit are not equal to each other, so the limit doesn't exist, so this function can't be continuous. However, it is right continuous. It's right continuous because the limit from the right actually attains the value that the function is equal to. On the left, the limit does exist, but the function does not attain that value. It attains this value, whatever that happens to be. For different values of c, you'll find that it's always going to be right continuous, but there's only one value where it's right continuous and left continuous, and that's the value that we just discovered, which is 9 over 7. When c is equal to 9 over 7, the function is both left continuous and right continuous, and basically what that means is that the two pieces of the graph meet up when x equals 2. That's what you need in order for a function to be continuous. You need the pieces to meet up. Another type of discontinuity is what is called an oscillating discontinuity or an oscillatory discontinuity. This is the type of discontinuity you get when the function just oscillates out of control. So for example, f at x equals sine of 1 over x. Notice that x equals 0 is not in the domain of this function because it's not in the domain of 1 over x. So we can't just plug in x equals 0. So that's not in the domain. But the question then becomes, what is the limiting value if it exists? Is this a removable discontinuity? And if you look at the graph, you can see that it is not removable. This graph oscillates out of control as you get closer to 0. And so the limit as x approaches 0 does not exist because sine of 1 over x approaches not just one value as x goes to 0, but it approaches infinitely many values as x gets close to 0. The value of sine of 1 over x approaches every single value between -1 and 1 that you can see on this y-axis. That means that there's no way to assign a value to the limit because all of these output values aren't getting close to just one number. They're getting close to infinitely many numbers, all of the numbers between -1 and 1. Since the limit doesn't exist, we can't redefine it, so it's not a removable discontinuity. In this case, it's called an oscillating or oscillatory discontinuity. As a remark, the substitution rule for polynomials and rational functions says that if f at x is a polynomial or a rational function, then the limit as x approaches a of f at x is equal to f of a for any a in the domain of f. This means that a polynomial is continuous at all a, and a rational function is continuous at a as long as you're not dividing by 0. That is, as long as x equals a is not a vertical asymptote. So a rational function and a polynomial are both continuous on their entire domain. These aren't the only functions. The trigonometric functions, the exponential functions, and the logarithmic functions are also continuous at every point of their domains. Let's talk a little bit about the intermediate value theorem. This is a theorem about continuity. Continuity on an interval. Let f be a continuous function on the closed interval from a to b. If z is some number that is strictly between f at a and f at b, then there is at least one number c between a and b such that f at c is equal to z. So we have a picture here. Suppose that we know what the graph looks like to the left of a, and we know what the graph looks like to the right of b, but we're not really sure of what the graph looks like between a and b. We know what f of a is. It's down here. And we know that f of b is up here. And we know that this function is continuous. Well, the intermediate value theorem tells you that if you pick any value that is between f at a and f at b, let's say we'll call it z, the intermediate value theorem tells you that there is some input that will achieve that as an output. And we can see that if we just look at the graph. So there's some c between a and b such that the output corresponding to that c is the given z. What's important to understand here is that it's not just this one particular z. Any values between f at a and f at b will be output values for the function. So if I were to choose a different z value, well, let's leave this z in here, and let's just change the color. So if I was to choose another z value, say down here, then I could find another input value that gives me that z. C. But in fact, not just one, there's one over here too. So there's two, and in fact, there's not just two, there's three. So here's another possible c value. What the intermediate value theorem tells you is that for any output value between f at a and f at b, for any output value that you choose, there will be some input value that gives you that output, and in fact, there might be more than just one. This is only true if you're looking at a continuous function on a closed interval. What that means is that if the function is continuous, the different pieces of the graph must connect to one another. So I have a piece of this graph to the left of a, and I have another piece to the right of a. And if the function is continuous on the closed interval from a to b, then that means that the graphs must connect in some way. What we've drawn in here is one possible way that they might connect, but they could connect in another way. But in order to get from the dot corresponding to a to the dot corresponding to b, the graph must pass through every possible output value between f at a and f at b. We can think about this in terms of drawing the graph. If a function is continuous, that means that its graph can be drawn without lifting your pen off the paper. So if I know that the graph to the left of A is down here, and to the right of B is up here, then I need to be able to draw the graph from A to B without lifting my pen off the paper. And if I do that, it doesn't matter how I draw the graph. If I pick an output value z and draw a horizontal line, then you can see that then no matter how I draw this curve, it must pass through that horizontal line. if this is to be a continuous function. And passing through that horizontal line means that there is some output that is equal to z. And every place where that horizontal line crosses the curve, that corresponds to an input value. So for this green line, there's exactly one, right here, there's exactly one input that will give you that output. But this orange curve, for example, there are several places where it crosses this horizontal line. Right here, 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 and here. And each x value that corresponds, so in fact, x equals 0 gives us that value, this value right here, every single one of these gives you a different c value. So there might be many, or there might just be one. Each one of these x values is an input that will give you z as an output. Let's look at an example. Show that the polynomial function f at x equals x cubed minus 3x squared plus 4x plus 37 has at least one real zero. Notice that no interval is given to us here. We know that a polynomial is continuous over its entire domain. All we really have to do is find some value that we can plug in here that will give us a positive number and a negative number, and then that means that there must be some value in between where you get 0. Let's actually do it. Let's just pick a number. Let's make it easy, x equals 1. F at 1 is equal to 1 cubed minus 3 times 1 squared plus 4 times 1 plus 37. So what is that? That's 1 minus 3 plus 4 plus 37. So that's 39. Okay, well, what if we pick, say, x equals, let's go with negative 3. So f at negative 3 is equal to negative 3 cubed minus 3 times negative 3 squared plus 4 times negative 3 plus 37. Now this might seem like it's difficult to compute. I chose negative 3 because this becomes negative 3 cubed, which is negative 27, and then this becomes positive 3 cubed, which is 27. But there is a minus sign here, so we're just going to end up doubling it. And then this one is minus 12. And so now we can add all of these things together, and we'll get here, we're going to get a negative 66. And then if you add 37 to that, you're going to have a negative number, which I believe is negative 29. Now the actual value here isn't that important. What is important is the fact that it's a negative number. So f at 1 is greater than 0, and f at negative 3 is less than 0. So we have a number which is bigger than 0 that's an output, and we have a number which is less than 0 as an output. That means 0 is in between these two values. 0 is in between these two values. So that means that since this is a continuous function, there must be some input between negative 3 and 1 that gives 0 as an output. Let's write that down. Then there is a number c between negative 3 and 1 such that f at c is equal to 0 by the intermediate value theorem. Let's just abbreviate it, IVT, the intermediate value theorem. Now this theorem doesn't tell us what the value of c is, it just tells us that there is a value of c. What we could try to do is we could try to narrow it down by picking numbers that are closer and closer together. We know that the value is between -3 and 1, so you could start picking other values. You could check other values between -3 and 1 and try to narrow it down that way. The graph of this function, y equals x cubed minus 3x squared plus 4x plus 37, it turns out crosses the x-axis at around -2.293. And where it crosses the x-axis, that's where it has a 0. That's where that function has a 0. Let's look at one more example. Let's show that there is at least one x value for which cosine of x is equal to x. We won't be able to find it necessarily, but we can show that there is such a value. How's this going to work? Well, we're going to start by defining a function. So define a function f. So I'm going to write f at x is equal to x minus cosine of x. What I want to do is I want to show that there's some value where this is equal to 0. Because if there's some value where this is equal to 0, then that means the difference is 0, so x and cosine of x must be the same. So this is our definition. This function is continuous for all values of x. So let's just try different values. Let's say x equals 0. F at 0 is 0 minus cosine of 0. Cosine of 0 is 1. So this is 0 minus 1, which is negative 1. So that's, in particular, it's a negative number. Let's try something like x equals pi over 2. F at pi over 2 is equal to pi over 2 minus cosine of pi over 2. Well, cosine of pi over 2 is 0. So this is pi over 2 minus 0, which is, of course, pi over 2. What's important here is not the actual value, but the fact that it's positive. F at 0 was a negative number. F at 0 equals negative 1. It's negative. And f of pi over 2 is pi over 2, which is positive. So we have a negative number and a positive number. So by the intermediate value theorem, there is some number, maybe even more than one, but there is at least some number c such that f at c is 0. Again, why do I know this? I know that f of 0 is equal to a negative 1. F at pi over 2 is equal to positive pi over 2. So that means there's some number c between 0 and pi over 2 such that the output is equal to 0. Because this is a negative number and this is a positive number. So if I pick any z between here, like say 0, then there exists some c between 0 and pi over 2 such that the input c gives me the desired output. So I can even say there is some number c between 0 and pi over 2 such that f of c is equal to 0. So what does that mean? Well, f of c is equal to c minus cosine of c. And that's equal to 0. So c is equal to cosine of c. So x equals c is the desired value. Remember, we were asked to show that there exists at least one x value for which cosine of x is equal to x, and we found one. Well, we don't know the actual value. We know that one exists. The intermediate value theorem tells us that some value exists, but doesn't tell us what the value is. It tells us that it's between 0 and pi over 2, but that's the best we can do. If we want to do better, we need to choose more values that are closer to each other. We could check pi over 4, for example. That's halfway between. And if the value was positive or negative, that would give us a better idea of where the value of c was. And then we could divide that interval in half again and again and again. And you just keep checking different values, looking at the outputs, whether it's positive or negative, and you can just narrow it down that way. Or we could look at the graph. The graph of y equals x minus cosine of x crosses the x-axis at approximately 0.739, which is right here. That means that the graphs of y equals x and y equals cosine of x intersect at that value of x, which is approximately 0.739. One way to think of this problem is that we know that cosine of x is always between minus 1 and 1. And we also know that x is not so restricted. X can be any value, bigger than 1 or less than negative 1. And we know that these graphs are continuous. That means that there's no erratic jumps or gaps or holes. So if I know that y equals x, at least eventually is bigger than 1, and I know that on the left side it's for far enough left, it's less than 1, and I know that cosine of x is always between minus 1 and 1, then I know that eventually this graph has to cross. And that's really what the intermediate value theorem is telling you. It's telling you that if you have continuous functions, then in order to get from one place on a graph to another, you can't lift your pen. And if I know that cosine of x is happily traveling along here, like this, between minus 1 and 1, and I have this curve y equals x, I know at some point it must pass between minus 1 and 1, and when it does that, somewhere it needs to cross the graph of cosine of x.